Okay, so hi everyone and welcome. We are very happy to have here today Luke Jones. Luke just got the PhD a few months ago from UC San Diego, and now he's an Einstein Fellow in Berkeley. And he will tell us about, he's an expert on flavor conversions of neutrinos, both in astrophysical environments as well as in the early universe. And he will tell us today about oscillating particles in supernova and then hydrogen at the cosmic dawn. Go ahead, Luke.
All right, so thank you everyone. Thank you for being here. So I will be talking about two disparate topics in astrophysics, but they share in common some underlying microphysics, namely particle oscillations. So as you just heard, those two topics are neutrinos and supernovae and hydrogen at cosmic dawn. And what I'm going to do is jump straight to what the main takeaways will be. So what we'll see in the first half, or maybe 2/3 of the talk, is that the dynamics of core collapse supernovae might be substantially affected by collective neutrino oscillations. But while we suspect that might be true, we don't know what the effects actually are. So I'm not going to shy away from the fact that this is an open problem, and instead what I'll do is report and even speculate on some new approaches. And I'm going to try to build in a brief pause for questions at the end of that part. And then in the latter part of the talk, we'll turn our attention to 21 centimeter cosmology. So in 2018, EDGES became the first experiment in this field to make a detection. It appears that they genuinely observed cosmic dawn, which is the turning on of the first stars, but their measurement has an anomalous feature that is plausibly interpreted as indicating a much lower hydrogen gas temperature than expected. So this has given rise to a number of ideas, and I'll talk about a way to account for this anomaly that hinges on hydrogen oscillating into a mirror hydrogen state. So that'll be the second part of this talk. But neutrinos come first, and we'll just start with the basic ingredients here. So, I mean, first of all, it's well known that oscillation frequencies are proportional to mass squared differences, which means you can infer these quantities by looking at how the probability of detecting a certain flavor varies as a function of propagation length or neutrino energy, which is actually the case in CAM land, which is being shown here. But the important thing for our purposes is that the oscillation pattern reveals delta m squared, mass squared splitting. Now, in medium, the masses of neutrinos are effectively changed by forward scattering on background particles. So there's no momentum transfer in this process, but it does affect the quantum phase evolution of the neutrino. And it does so in a flavor dependent way. So suppose that the background is made up of electrons. Nu E then interacts more strongly with the background than the other flavors do. And so it experiences a larger change in its mass, a larger effective change. But now mass differences have changed, right? Not just the masses, but mass differences, and therefore oscillations have as well. And, you know, indeed, we expect forward scattering on charged leptons to show up in the neutrino signal from the next nearby core collapse supernova. And it'll do so, moreover, in a way that depends on the neutrino mass hierarchy, which is not decisively known at present. So here we're seeing the anticipated signal for a single event. As detected by Super K, Dune, and Juno, we're really just kind of zooming in on the neutronization burst here. So the red curves are the prediction without oscillations taken into account, and the blue and green curves are for the normal and inverted mass hierarchies, respectively. So main point here is the differences are significant. And similarly, neutrinos forward scatter on other neutrinos. But here our understanding of the phenomenology is on considerably less secure footing. So the flavor evolution of any given neutrino, like this one, depends on the flavor states of all the neutrinos that it crosses paths with. And as a result, the oscillation problem becomes a nonlinear one, and one that's capable of supporting various kinds of collective behaviors, because each of these neutrinos is oscillating and forward scattering on other ones. So this is the governing equation. Without getting into too much detail here, it describes how the neutrino flavor field evolves under the influence of three different things, really: particle streaming, a Hamiltonian that encodes vacuum oscillations, and forward scattering, and also collisions. So rho here is the density matrix. It's a 3 by 3 matrix because there are three flavors, but it's also a field with a matrix value everywhere in phase space. So, hundreds of papers have been written on this equation because in general, it's very difficult to solve, and it gives rise to a rich array of behaviors. I've listed a few review papers here, and I especially draw attention to this very recent one by Irene Tambor and Shashank Shalgar. So, the challenge is to solve and understand neutrino quantum kinetics in core collapse supernovae, which means that we have to model the supernova environment. We have to find some way of modeling it. Well, let's set aside oscillations for one moment and talk about core collapse supernovae from the viewpoint of cutting edge radiation hydrodynamics simulations. So the basic physics is that stars more massive than about 8 solar masses collapse in on themselves once they've run out of nuclear fuel in their cores. The collapsing core of the star then bounces or rebounds due to repulsive nuclear interactions, and the bounce launches a shock wave into the outer parts of the star, which are still infalling. So in this upper left figure, we're seeing the radius, the mean radius of the shock as a function of time after core bounce. And for a period, the shock stalls at 100, 200 kilometers, something like that. So in the lower right, this is kind of a snapshot from that phase. The shock is shown in light blue. Here we're seeing particle trajectories over the past 5 milliseconds, I think. So, stellar material is continuing to rain down on the shock from outside, but behind the shock is a turbulent fluid that's essentially being boiled from below by neutrino heating. And the fluid starts to sort of spill outward, eventually being launched into explosion. So here's where the shock really takes off. And I mean, the whole thing is a complicated affair, and solving the quantum kinetic equations in this setting, I'm going to go out on a limb here and say is probably hopeless without employing some well-chosen approximations. So that's my framing for this whole problem. And for a number of years, our knowledge of oscillations in core collapse supernovae was based on the bulb model, which is being illustrated here. So the bulb model makes some frankly bold assumptions. So the supernova is spherically symmetric and stationary on timescales of relevance for neutrino oscillations. And neutrinos are assumed to be emitted isotropically from a sharp decoupling surface. So strictly from a computational point of view, I mean, these assumptions simplify the problem tremendously. So now, for some given representative time, one just needs to solve an ODE in 3 independent variables. And so, this can be done, and the bulb model is, I would say, is valuable because it models the supernova globally in a way that's both solvable and self-consistent. Self-consistent meaning that the results of this model don't suggest anything that undermines the assumptions of the model. But unfortunately, it now appears that none of these approximations is quite reliable. So that's something we're going to come back to in a moment. But nonetheless, I mean, what do we learn from the bulb model, such as it is? Well, as far as the impact on explosion, which is really what I'm focusing on in this talk, as far as the impact on explosion, the effect is predicted to be very small for the simple reason that although collective flavor transformation does occur, it only sets in at radii that are well outside of the region in which most neutrino energy deposition takes place. So in other words, these black squares, which is where flavor conversion starts to become significant, they at all times lie well outside of this hatched region, which is where 75% of net neutrino heating is taking place. So the conclusion, oscillations don't significantly change the energetics in the bulb model. But as we're about to see, this conclusion is possibly in need of revision for real supernovae because of the model's inadequacies. Now, rather than trying to solve a global and necessarily simple model of a supernova, we can adopt a complementary perspective and ask which kinds of solutions are supported by the linearized equations of motion at a given time and location. So specifically, what we want to know is whether perturbations in the flavor field are going to grow. These are sort of perturbations away from the classical transport solution, what you might get out of one of those rad hydro simulations. And so this is a complementary perspective, and it's taught us a number of things. It's taught us that breaking the symmetries of a model, even very slightly, leads to new instabilities. So that's why we suspect that results based on the bulb model may not be reliable after all. The most alarming discovery, I think, has been this whole new class of instabilities called fast flavor conversion, or FFC. This is probably a little bit in the weeds, but FFC is associated with zero crossings in the electron lepton number carried by neutrinos as a function of propagation direction. So it's easier to just see this graphically. For instance, if the flux of nu E bar, so kind of comparing the red and blue curves here, if the flux of nu E bar is greater than that of nu E in more radial directions, but less than it in more tangential directions, then FFC is liable to occur in this region. Just, I guess, a point of note, the word fast here is kind of being used in a technical term. Fast refers to the fact that these effects operate proportional to mu inverse, which is essentially G Fermi times the number density of neutrinos. And in a supernova, this means that the effects are occurring on length scales of millimeters to meters and time scales of picoseconds to nanoseconds. So very fast and small indeed. Now, do the requisite conditions for these instabilities show up in simulation data? Multiple studies now indicate that they do, at least in some cases, some of the time. This is something that people are still exploring, just searching for instabilities, trying to assess what the prevalence of them is. you know, this isn't totally exhaustive, but instabilities have been located both in the convective layer of the protoneutron star. So we're looking at, you know, radii of like 10, 20 kilometers, that sort of thing. And then, you know, in and also beyond the neutrino decoupling region. So in the top figure, the yellow contours here are showing where the lepton number changes sign, hence where fast instability is expected for reasons related to what I was just describing with these ELN crossings. And then in the bottom figure, starting in this instance around 50 kilometers, instabilities can again be found. It's a little bit hard to see here, but there are white X's marking instabilities. So, you know, we think instabilities, including fast ones, or maybe I should say particularly fast ones, may be an issue and may in fact affect explosion, contrary to what the bulb model had predicted. So now let's talk about what it will take to do an oscillation calculation that isn't based on severe and possibly unreliable symmetry assumptions. So this will be the last subsection of this part, computing oscillations. Well, a bulb model calculation, just to say it again, solves an ODE in 3 variables: radius, neutrino energy, and neutrino propagation angle away from the radial direction. In contrast, a fully asymmetric calculation what adds time for one thing, and also 2 other spatial coordinates and 1 other momentum coordinate. And each of these compounds the problem of resolving oscillations. Each one compounds the problem. You know, it's easy, I think, to appreciate why resolution in time or space might need to be high. That's just because oscillations take place on small scales, as we've seen, small spatiotemporal scales. But why does resolution need to be high in momentum space, particularly angular resolution? So this question really kind of gets to the heart of how neutrino quantum kinetics differs from radiative transfer, which is to say neutrino transport without oscillations, or neutrino classical kinetics, if you will. So in a radiative transfer treatment, each flavor satisfies an equation like this one. So this might be the specific intensity of nu E, for example. And roughly speaking, the left-hand side leads to more forward-peaked angular distributions as one moves further away from the source, simply by virtue of the fact that the source is of finite size. So it looks like everything's radiating out from a point. Whereas the right-hand side leads to more isotropic distributions. So these are, scattering, absorption, and emission taken collectively. Those tend to isotropize. In contrast, oscillations de-isotropize flavor. They create small-scale structure in momentum space, as we're going to see more of. So, and I should note, these observations I'm making here are computationally significant. Some of the frontier rad hydro simulations use what are called moment methods, in which just a small number of angular moments are evolved. And those methods work because the neutrino angular distributions transition as radius increases from an isotropic diffusion limit. So here, like this outer, nearly circle is at 30 kilometers in radius. They transition from this isotropic limit to a forward-peaked free streaming limit. But since oscillations, unlike collisional processes, are not isotropizing, as we were just noting, it needs to be asked whether this nice feature of the problem can be salvaged once oscillations are included. The nice feature being that one can truncate and close the moment expansion, keeping only a manageable number of angular moments. So there is, I would say, suggestive and encouraging evidence that that collective oscillations are principally associated with low L dynamics. L here being the referring to the Elf Legendre moment of the angular distribution. So this is an encouraging fact if you're trying to use a moment method like what is used in rad hydro simulations. This statement had already been established for slow collective oscillations, just recently, my co-authors and I have argued that it's also true of fast flavor conversion by showing that the equations of motion exhibit a pendulum-like structure primarily involving low L moments. So I'm not defining these quantities here, but each of them is built out of the first few angular moments of the neutrino and antineutrino density matrices. And we have found numerical evidence that pendulum-like evolution in the flavor field is indeed the dominant feature, at least on short time scales. So the oscillations are anisotropic. Let me take a moment to explain this. So here we're seeing how flavor changes as a function of propagation angle on the horizontal axis over the course of a single fast collective oscillation. So we're seeing half a period of a fast collective oscillation, and this is color-coded in time. And the collective oscillations depend qualitatively on the angular distribution. So alpha is the parameter here, and this it also means that collective oscillations depend qualitatively on the radius. So radius 33 kilometers, radius 70 kilometers. They look quite different. And although there are sometimes fairly sharp features as a function of angle, all the major features are nonetheless captured by the first few moments, which is what we expected on the basis of analytic arguments. So sort of restating, I mean, we understand that in certain idealized limits, collective oscillations are well approximated by pendulum-like motion, the pendula being, again, representative of aggregates of neutrinos. And this is true, I should emphasize, even in asymmetric environments. But these solutions don't capture everything. There are also non-periodic effects associated with the transfer of power across scales in phase space. So here, for example, we're seeing power cascading down to smaller angular scales and forming features that are somewhat reminiscent of turbulence. If you time average this over relatively short periods, you'll see these curves really flatten out. You get this kind of inertial range-like behavior, to use fluid language. So, I mean, this figure is one way of visualizing the de-isotropization that I was talking about earlier. Small-scale features are progressively being generated. And just a reminder, so L, again, this is the Elf Legendre moment of the angular distributions. So we're working in momentum space here. As it stands, we mainly have empirical observations of these non-pendulum-like behaviors, and empirical in the sense of numerical experiments, of course. And so an ongoing priority, in my opinion, is to develop the basic theory of them, the basic theory of these non-periodic behaviors, which are not captured, for example, in this body of work. So let me put the challenge this way. The challenge I'm referring to, so each neutrino is an oscillator, right? Each neutrino oscillates. The question is, how does a system made up of many oscillators evolve in phase space? This question was actually addressed by the esteemed astrophysicist Donald Lynden-Bell. He observed that even if the oscillators are frictionless and non-interacting, just take the simplest possible case, they'll still approach equilibrium in a coarse-grained sense by creating structure below whatever the resolved granularity in phase space is. So that's what's being illustrated here. You kind of have this initial region in phase space, and the oscillators that he's assuming have some energy dependent period. So they kind of spread out and wrap around at 2 pi, and eventually, you need a kind of microscopic resolution to see that this isn't just a system in equilibrium. I mean, that being said, why did Lynden-Bell choose to write about this of all things in one of his classic papers? So the reason is that he was developing the theory of collisionless relaxation in galaxies in the paper I'm citing here, and he wanted to illustrate just how general and fundamental collisionless relaxation is. So he used this oxymoron, violent relaxation. He used that term to describe how it works in gravitational systems. It's also closely connected to what is sometimes called filamentation in plasmas, and even in some sense to turbulence in fluids. And collisionless relaxation happens in neutrino kinetics as well, but we are still developing the techniques to describe it. So that's another way to put where we are with this problem. And in addition to being relevant to the actual physics, collisionless relaxation is also relevant, or I go so far as to say central to the numerical side of neutrino kinetics. So here's an example of what I mean. The figure is showing 2 calculations that differ only in the number of moments that are being evolved. One of them uses 6,000 moments, the other just 200. And the calculations agree up until power, flavor space power, hits the 200th moment, at which point error from truncating the moment expansion propagates back to lower L. So we're seeing this, we're seeing the error already beginning to propagate backward here. And it's then not long until the calculation becomes totally erroneous. Power starts to artificially kind of build up and leads you very much astray in your numerical results. So on an earlier slide, I posed the question, why is angular resolution an issue in computing neutrino oscillations? And the answer I've given is that oscillations create small scale angular structure, right? But that's really just half the story, because it's not obvious a priori that that the small scale details are actually important. As a matter of fact, I don't think they are. But here's the other half of the story. Even if the amount of power at small scales, like L equals 200, is minuscule, even if it's down by 10 orders of magnitude or something like that, from the scales that you actually care about, it has an outsized and ultimately disastrous impact because of this sort of back reaction, the back reaction of high L, very high L onto low L in finite time. And incidentally, this problem isn't unique to neutrino kinetics. It afflicts other weakly collisional systems too, and it's actually been a subject of study in plasma physics going back to the 60s or 70s, basically since people first started to trying to solve weakly collisional or collisionless kinetic systems on computers. So various strategies have been devised in the plasma context. Things like artificially damping power at small scales before it's able to back react. You could imagine trying to sap power out before it's able to sort of reflect at the boundary. But personally, I haven't done any kind of systematic study of how well those strategies work in the neutrino context. I think they're potentially promising, I guess I would say. I will note, mainly for the experts, those who work on oscillations, that the problem I'm describing on this slide is, I believe, distinct from what has usually been meant by spurious instabilities, which have also kind of plagued us for a long time. Now, let me emphasize that over these last several slides, I've been focusing on the dynamics in momentum space, but there's still this issue that oscillations occur on small spatiotemporal scales. So let me close out this part of the talk with, frankly, just a bit of speculation. So computational fluid dynamics is often faced with, I think, a similar issue at high Reynolds number. In that case, it's simply not possible to resolve the turbulent dynamics at all scales. There's a large separation between the scales of energy injection and energy dissipation. And so practitioners, I understand, resort to techniques like time averaging and coarse graining. Just as in momentum space, one encounters a closure problem here as well. So for example, the filtered Navier-Stokes equation, this is a kind of averaging or coarse graining at some grid scale of the Navier-Stokes equation. It depends on a subgrid scale stress tensor, which is hiding subgrid correlations in the velocity field, right? So there are still correlations hidden here, and computationally, what one has to do is prescribe some kind of closure, basically make an educated guess or compute an educated guess. And so, for example, a closure might kind of on physical grounds assert that the effect of subgrid physics on the resolved scale is to, just to add sources of viscosity and pressure. And this is a standard approach, as far as I understand it, to calculating fluid flows, and it's apparently pretty successful. So, so here's the speculation. I mean, why not do something similar for flavor evolution? Now, I haven't actually pursued this line of thinking very far. So here I just want to kind of put the idea out there and also indicate the disanalogy that I think makes this task daunting. So in fluid turbulence, convection transfers energy to smaller scales until microphysics, namely viscosity, becomes important and is able to dissipate the injected energy. But let's contrast this with flavor evolution, right? So convection, in this case, convection and microphysics both transfer energy across scales. And the microphysics here, which is this combination of oscillations and nonlinear forward scattering, it is, well, again, nonlinear, but in addition to that, it's also non-randomizing, right? So unlike diffusion, its tendency isn't to smear out structure. Yeah, so I made this point earlier in reference to momentum space, but it's true in coordinate space as well. So I think, more work is definitely needed to figure out how to implement filtering type ideas in the flavor context, but I mean, clearly something like this would be extremely useful, given that there might be, something like 6 orders of magnitude separating the oscillation length from the supernova scale height. So it's worth thinking of strategies like this, I believe. Okay, so I'm going, let's check the time real quick. So I'm going to briefly summarize this part of the talk, and then I think I'll pause for a few moments to see if there are any questions or comments before I move on to 21 centimeter cosmology. Okay, so you know, our theoretical understanding of oscillations in core collapse supernovae is mostly founded on these first two approaches, highly simplified models like the bulb model, and linear stability analysis. This talk thus far has been inspired by wanting to make a third one viable, which I'm calling realistic quantum transport. But you know, if I've given the impression that the oscillation problem is still quite open, I mean that's because it is. But the stakes for supernovae are high, and so I haven't gone into this in great detail, but oscillations are a missing piece of the physics in simulations, and they likely have ramifications for well, for the dynamics and explosion of supernovae, which is the thing I've been highlighting to some extent here, as well as for the nucleosynthesis that takes place in these environments and the neutrino signals that might be detected from them. So let me pause at this point to see if there are any questions or comments up to this point.
So I have a question meanwhile the others think about what to ask. When you talk about the time in which those like noisy features develop in at higher L, which is the realistic time scale within which more or less they should develop?
Yeah, so these, so let me go and see if I can go back to the figure here. So the time scale at which let me go back to this one, in fact. So the issues start to happen basically as soon as you hit whatever L max is, whatever the truncation point is. Now, the cascade happens on a fast time scale. So there's an interesting kind of fact here, which is that physically, this effect may not actually be that important. The cascade may not be that important on timescales that we care about because although it's moving out at a rate mu, it's still down by several orders of magnitude and in amplitude and in power. So the amount of power that's being lost at low L may not actually be that significant. However, regardless of the amplitude, this is kind of the point to emphasize, I think, is that regardless of the amplitude, the fact that this spreads out at mu means that it can very quickly get out to the truncation point and reach back, at L equals 0 or a few. Now I should be more specific and say it's proportional to mu. I actually don't have a way to, if you just gave me the initial conditions, I don't at this point have a way to sort of just predict the time at which it will cause issues.
Yeah, I was just wondering, because if it relaxates, like it develops and those structures grow on timescales that are larger than the typical astrophysical scales, then of course also the other conditions would change. And so maybe this problem becomes, it cures itself in a sense, but it doesn't seem so. And the other question that I also have is, so in principle, this could be kind of smoothed or partially solved also by collisions. What do you think?
Yeah, so I think, and I'll say for the sake of the audience, that Irene and Shashank have made this point that they've actually, I think, observed, if I'm correctly characterizing your recent paper, they've observed that collisions can actually help numerical properties, and I'm thinking that may have something to do with damping these features. I think my concern is still that realistically, it would be nice to be able to get away with like a few angular moments, but given how weak collisions are in, outside of the neutrino sphere, I think that while this may help somewhat, I don't know if it fundamentally changes the problem from a computational perspective. And just to kind of like quickly answer your previous question more directly. So this was, I didn't put units, that these are in units of omega inverse. So if omega is a length scale, let's say of a kilometer or something like that, then this could be sub-kilometer scale. And already with 200 moments there, you're starting to have issues. So I think that inhomogeneity probably will not, in any sense, kind of like wipe out this problem.
Thank you.
So Luke, I have another comment regarding the last point you made before the summary slide. And if you look at a recent paper by Ian, that is basically what is done in the paper, right? There is a coarse graining over the spatial grid, and that leads to pretty interesting results. We don't find any cascade due to these small scale inhomogeneities.
Okay, interesting.
So are you aware of this paper by Ian?
Yes, I mean, so are you solving the coarse grain degrees of freedom, or are you doing coarse graining?
We do coarse graining.
Yeah.
Oh, very interesting. Okay, I'll have to take a
look at
closer
the
look.
appendix of the paper.
Okay, thank you.
More questions?
Okay. All right, so there are no more questions on that for now. I'm going to shift away from supernovae to talk about a different problem. Although we'll see soon enough that similar microscopic physics is involved. So the topic now is 21 centimeter cosmology. So this field is premised on the fact that photons coming from high redshift, CMB photons, for example, pass through clouds of neutral atomic hydrogen on their way to Earth. So some photons are absorbed by the hydrogen, other photons are emitted by it. For photons with wavelengths that are around 21 centimeters, absorption and emission are sensitive to the hyperfine structure of hydrogen. So just as a reminder, the hyperfine splitting arises because of interaction between the proton and electron magnetic moments. So its value for the ground state hydrogen is 21 centimeters as a wavelength, or about 6 micro eV as an energy difference. So to put the point maybe a bit simplistically, if all the atoms are at the lower hyperfine level, then absorption is favored over emission because there are many atoms that can be excited and none that can de-excite. But if you start to increase the fraction of atoms at the upper level, then emission becomes increasingly favored. Now, the fraction of atoms at f equals 1 to atoms at f equals 0 is conventionally quantified by the spin temperature. So higher T sub s means more atoms at the upper hyperfine level. And just to say it again, I mean, absorption and emission tell you about the spin temperature. And the key insight is that the spin temperature in turn tells you about various processes taking place in the hydrogen clouds. And that's because TS is a kind of weighted average of the brightness temperature of the microwave background, the kinetic temperature of the hydrogen gas, and the color temperature of the Lyman alpha radiation field. So I mean, the point here is 21 centimeter cosmology experiments, like EDGES, are aiming to infer the spin temperature of hydrogen at high redshifts. That's the goal. And in 2018, EDGES announced that they'd succeeded in this goal. So, I think it's fair to say the era of 21 centimeter observational cosmology has officially commenced. And intriguingly, it's already turned up an anomaly. So what did EDGES observe? This figure is, so this is actually showing the differential brightness temperature, T21, which is closely related to the spin temperature. And between redshifts of about 15 and 20, the EDGES signal shows a dip below 0, which means that the spin temperature is colder than the background radiation temperature. The spin temperature is colder. So seeing an absorption feature was not unexpected for reasons that I'll explain on the next slide, but the depth of this feature did come as a surprise. And the discrepancy is at the level of about 3.8 sigma. So let me explain why an absorption feature was expected, and then we'll discuss ideas that might account for it being anomalously deep. So this goes back to really kind of back to the goal of 21 centimeter cosmology, which is to observe the long period between recombination and the end of reionization. During that period, the first stars turn on. That stage is called cosmic dawn, and that brings to an end the cosmic dark ages. So cosmic dawn, when these first stars turn on, is also when the edges dip first starts to appear. This corresponds to the edges dip. The reason that happens is that stars are injecting Lyman alpha photons that indirectly couple hydrogen atoms to one another. So basically photons from stars are bouncing around from atom to atom. And that drives the spin temperature away from the background radiation temperature and toward the much colder hydrogen gas temperature. So what I'm describing is called the Valheisen field effect. And it's what accounts for this dip. Well, then, once enough stars have formed, their radiation actually begins to heat up the gas, and that terminates the absorption feature. So the physics that underlies this figure is pretty subtle, I think, and I'm not an expert in this area, but the important thing here is that the height of this absorption feature, the height is at most the difference between the background radiation temperature and the hydrogen gas temperature. Okay, so with that in mind, what could account for the anomalous depth? Well, it's a complicated experiment, and foregrounds have to be modeled and so on. So maybe systematics are an issue. I mean, there has been some discussion about that, of course. But let's just say we believe the signal that EDGES is reporting. Explanations then mainly fall into two categories. Either there's unexpected astrophysics that makes that's making the background hotter, for example, accretion onto early black holes, or there's BSM particle physics that's making the gas colder. Again, we're trying to increase the difference between the background and the gas. And so as an example in this last category, a much discussed proposal is that there's scattering between standard model particles and dark matter. So this proposal has generated quite a lot of interest, and the basic idea behind these kinds of scenarios is that the baryonic gas, the hydrogen, loses heat to dark matter, which is taken to be colder than the gas. And this explanation was actually put forth along with the original detection announcement by EDGES, but further study has shown that the explanation, how should I put this? It, I guess, isn't quite as appealing as one might have hoped at first. It turns out that the simplest scenario is strongly constrained by fifth force experiments because in this scenario, hydrogen has to have a net overall charge, coupling it to a new light mediator. Now, an alternative is to let dark matter be millicharged. That is, so dark matter has some small electric charge, but it could only be a small fraction of dark matter that carries charge, and even then the scenario is highly constrained. So millicharged dark matter still works. I should be clear, but it's worth exploring other possibilities. I see it's 10 minutes of the hour, so let me just try to hit the essential points here. Okay, so I've been working with Seth Corin, who's a postdoc at Chicago, on a different kind of BSM scenario that we believe can achieve the same effect of cooling the hydrogen gas prior to cosmic dawn, and therefore might explain the edges anomaly. So one of our guiding intuitions is that, well, suppose edges does indicate new physics, right? Maybe it should be taken as a hint that the new physics has thus far only shown up in connection to neutral hydrogen. Well, one of the things that's special about neutral hydrogen is that it's neutral, and so it can oscillate into a dark sector state without violating any gauge symmetries, much like how a standard model neutrino can mix with a sterile neutrino unproblematically. Now, of course, hydrogen is also a composite particle, which means it's not totally obvious why there would be mixing between it and a dark sector state. But there is a well-explored model building framework in which this makes sense. It's the framework of mirror models in which there's a copy of the standard model particle content. These kinds of theories go back a long ways to Li and Yang in the 1950s, thinking about how to restore space-time parity as a symmetry. I think what I will do in the interest of time is kind of skip some of the more particle physics based elements here. Really, there's a lot to say about motivations for postulating mirror models and leptoquarks, which make an appearance in a UV completion we propose. But for our purposes, I think we can say that we're invoking them because they offer plausible particle physics underpinnings for hydrogen oscillations. So let's just, in the remaining few minutes, talk about what the cosmology of hydrogen oscillations looks like. So this is kind of in one diagram how the mechanism for cooling. So hydrogen oscillates into mirror hydrogen, H prime. We're assuming that that unlike standard model hydrogen, H prime does interact with the dark matter. So then H prime scatters on dark matter, which is cooler than hydrogen. And this causes H prime to lose kinetic energy, and then it oscillates back into H, now carrying less momentum. So hydrogen is effectively or indirectly being cooled. Now this sequence should only be efficient at certain times. Going back to the pre-recombination universe, hydrogen is all ionized and it can't get through the mixing portal. We're assuming, moreover, that the mirror sector is not significantly populated at early times. It only becomes populated once hydrogen starts to oscillate into mirror hydrogen. So early on, there's no influence from this mirror sector. We actually want to wait until after a redshift about 200 for the full sequence from the previous slide to become rapid. So sometime in this period between a redshift about 200 and before Z of about 20, before the edges signal, we want that sequence to become fast and therefore cool the hydrogen gas. Now, there's an important point here, which is that mixing should also stay in equilibrium through reionization, so that as the density of neutral hydrogen drops, so does the density of mirror hydrogen. They'll essentially track each other. And in that case, ultimately, we expect most of the baryons that were lost through oscillations to be recovered by the end of reionization. Now, I'll also go a little bit quickly through this. I mean, you may recall this equation. There is a quantum kinetic equation that's describing the dynamics, but we're not actually solving this equation. What we're doing is a kind of comparison of timescales just to make sure that the timescales do work out as we expect them to. And so this figure is just showing that for various choices of this mixing parameter, delta, you can, in fact, get the mixing equilibration timescale, gamma os, to exceed the Hubble rate only at the desired times. The dominant physics here, the dominant process is hydrogen-hydrogen scattering.
Luke,
And yep.
Shashank has a question. Shashank,
Yep.
go ahead.
Yeah, so I have a question. The H prime, which is the mirror hydrogen, does it have a baryon number?
No, and so I will. So what we're doing is we're introducing the global symmetries B plus L prime and B prime plus L. So there are mirror versions of baryon number and lepton number, and we are in the UV completion, we're introducing leptoquarks that are kind of charged appropriately so as to avoid particularly, rapid proton decay. But H prime itself does not have baryon number.
Okay, so basically you have a baryon number violating process, but you are engineering the whole particle physics theory so that it avoids proton decay.
That's right.
Okay, sounds good.
That's right. And so we've kind of done this comparison of timescales with the relevant terms in medium and scattering processes, and found that viable parameter space does exist in this scenario. So a number of considerations go into this figure that I'm not describing, although I'd be happy to do so, of course. But the main message I want to communicate is that if the mixing parameter delta and the H prime dark matter cross section both correspond to approximately cosmological timescales, then the full picture is consistent, which I think really was not obvious from the beginning of this project. So the scenario being presented here, is one in which dark matter has a mass comparable to the hydrogen mass and a cross section with H prime that is, roughly comparable to the hydrogen cross section. And we're looking at values of delta. Again, this is the mixing parameter, that are in the neighborhood of, something like 10 to the minus 37 GeV. And so, this turns out to be a nice energy scale for the UV theory we have in mind. Again, so this is kind of to your point, Shashank, but I think I'll actually mainly skip this, except to say that if you do a very kind of coarse mapping of the mixing parameter delta to the masses and numbers of leptoquarks in this kind of toy model, where we're suggesting you're actually led to what we're finding here is that, plugging in a mass scale, a leptoquark mass scale of something like a TeV or so, we're both in the neighborhood of leptoquark masses that are unconstrained by the LHC, and in the neighborhood of mixing parameters that are viable for explaining the edges signal. So I'm pretty much out of time here. The last two things I was going to mention, I'll just state very briefly. There is was this longstanding problem in astrophysics called the missing baryons problem. I think here I'll just note that, as far as we're aware, the hydrogen portal is the only proposed particle physics scenario that might predict that some of the baryons in the low redshift universe should be missing, if in fact mirror hydrogen doesn't completely reconvert to standard model hydrogen during reionization. So that's one thing. And I guess the other kind of takeaway here is like the uncertainties continue to be very large in observations of low Z baryons. And then the other, again, I'll just very quickly state this, the other is the formation of stars. So we do expect that as gas clouds collapse during the dark ages, H prime mixing will shut off. For a given delta, the mixing we expect to shut off once the density reaches the kind of the crossing point between the red and black curves. And then hydrogen, standard model hydrogen and mirror hydrogen will then evolve independently, except for gravitational interactions between them. And the thing I really want to draw attention to is what happens in the mirror sector. So all we have in that sector is mirror hydrogen, And so the chemistry plays out differently. Ordinarily, free electrons catalyze the formation of molecular hydrogen, which is an important coolant in collapsing gas clouds. And we suspect, in line with thinking by other authors, that the absence of H2 may lead to mirror gas clouds directly collapsing to supermassive black hole seeds because they're unable to cool and fragment into smaller stars. So the context here is that, you know, it's an outstanding question how billion solar mass black holes got to be that big within the first billion years after the Big Bang. And then another possibility, which is not, you know, these aren't mutually exclusive, is that there are just mirror stars. So, so to finish up, I'll return to the slide I showed at the beginning and say again, we've covered two different topics here, but I've grouped these together, of course, because they share this common denominator of particles oscillating in medium. So I'll end there, and thank you all for your time.
Thanks a lot, Luke, for this nice seminar. More questions or comments?
I have a question. Luke, what is the mass of the mirror hydrogen?
So we are assuming, for simplicity, that there is a Z2 symmetry. So the mass in the mirror hydrogen in that case is exactly the same as hydrogen. Probably, you know, what you're leading to is if you do have a mass splitting, it would have to be extremely small, so as not to significantly suppress the mixing even in vacuum.
Yes. And also what I'm thinking is, can it be exactly the same? Because even if you say it is exactly the same, you have to say it is exactly the same at a given energy scale, because there's going to be a renormalization group evolution of the masses, right? Due to higher order effects. So even if you say it is exactly the same, it can only be said at a given energy scale.
Yeah, I mean, that's absolutely right. And I mean, the issues here are really dark matter and I guess the inflaton, right? Because those are the important asymmetries. We are sort of agnostic to that aspect of the model building, but absolutely, if you have, if the couplings to dark matter or to, you know, whatever is going on at inflation, if they are breaking the Z2 symmetry, they open the door to possibly having different runnings of various parameters.
I mean, they have to be different because one is a standard model particle, another is not. But that actually, the reason I was asking is the following. If there is a mass difference, then just like in the case of neutrinos, wouldn't the medium affect the frequency with which these hydrogens can oscillate into mirror hydrogens?
Yes, and so that is one of the things that we're doing in this paper is calculating the various in-medium contributions.
Okay.
Yeah, so that the assumption is kind of that the mass splitting in vacuum is 0, but they acquire different in-medium masses, and that is that's important to kind of changing the to getting the right timeline.
Yeah, that I agree. But what I'm trying to say is that, but you cannot have a resonant effect because of that, because you don't have anything to go in resonance with. But if you have a small mass difference, then you have two mass scales available and you can have a resonant effect there.
Yeah, resonances are right. You could have resonances. We are choosing kind of like just the simplest possible mixing scenario in which that just doesn't happen.
Okay.
More questions?
I have one question. Thank you, Luke, first. And my question is, I was thinking if you have hydrogen and mirror hydrogen mixing, could you put some bounds on the mixing just from precision spectroscopy of hydrogen? So the transition energy should be affected just by the fact that the normal hydrogen can mix with the mirror one, right?
Yeah, I think that's right. And I would like to think about this more. I think one issue that arises is, like, anytime you just have hydrogen in a tank or whatever, you're going to have in medium effects. And the thing is, we're dealing with this energy scale that's 10 to the minus 37 GeV. So very, very weak interactions could totally dominate and shut off the mixing. There's a weird way in which, the fact that it's kind of amazing from that perspective that it does work out on cosmological scales.
Right. So you mean, like, even if you put like a lot of hydrogen in a tank and you start observing transitions, then the effects from normal physics would dominate over any potential mixing? Is that what you're saying?
Yes. I'm saying yeah. That's right. I think the in medium spectroscopic effects would be very, very suppressed.
Okay, I see. Thanks.
We have time for one last question.
I have one.
Go ahead.
I think because the mirror hydrogen is interacting with dark matter, shouldn't it form like more gas clouds around the dark matter ones as compared to the normal hydrogen?
Yeah. So this will depend on. Yeah, let's see. What do I want to say here? I mean, I think that will just depend on the chosen interaction with dark matter, but I do see a possibility for interactions to affect structure formation in the mirror sector.
Yeah, because you are saying that the mirror hydrogen can oscillate back to normal one. I think we can actually get some astronomical observations for that, maybe.
Yeah, no, that's very interesting. I'd be curious to hear more.
Thanks.
Okay, then we are running a bit beyond the time. Let's thank again Luke with a round of hands.
Thanks, everyone.
And thanks also for waking up earlier for us. It was very nice to have you here and to listen to your work.
My pleasure. Thank you.
Thank you, Luke.
Okay, so we meet again in 2 weeks.
That's right.
Bye, everyone.
Bye-bye.